So one thing to take note of is that this process, as you've seen from looking at past paper questions, just like having like a brief look to see what this question's like at the end of the paper, sometimes it's split up into Chi-Squared for the first part and then a sample means hypothesis test, normal distribution for the second part. Sometimes it can take up the full question, and subsequently is, a quarter of the paper. So it's one of those things that's quite easy to get a number wrong at some point. So you've got to have your wits about you and do this very carefully. So the idea with a contingency table test and contingency tables is that you're given a two-way table, okay? And let's say if you were doing this practically out in the real world, then the idea is that you're trying to see if there is some connection between different attributes, okay? So that is kind of a little bit more than just looking at two variables like we have done with the product moment correlation coefficient. We're looking at a two-way table, so there can be like 4 different options or 6 or whatever. And the way that we do it is we compare, as it says, the experimental or survey results. So you go out, you perform a survey, you collect your data, and what we're going to do is compare that with what we would expect to get if the variables were independent of one another. So the idea of probability independence comes up here. So what we're going to do is we're going to go through an example, and you've got this example on a sheet in front of you, okay? So I've got it all printed out so we don't have to kind of like go through and draw out big tables all the way through. So the situation is, the marketing manager at a theme park and zoo undertakes a survey of a random sample of 500 visitors. As part of the analysis, he categorises them according to the type of ticket they have bought. Tickets are available for children, adults or seniors, and there are 4 types of ticket available: theme park only, zoo only, combined 1-day pass, and combined 2-day pass. And what has happened now is that the manager's gone out and has collected that data, and we've got it in a table. Okay, now the first thing to do is to fill in the totals for the row and columns. Okay, that's the first thing to get right. So could you fill in those gaps in your table to start off with, please? Right, okay, so there's the first opportunity to go wrong. Right, so that's our first step. So we've got, and we should obviously, because the question said there were 500, there should be 500 in the bottom right hand corner. That's the big check that everything's gone correct from so far. Okay, so these are the observed values, okay? So what we do is, if we were to assume that there was no association between the type of ticket being bought and the person that's buying the ticket, we would be assuming that the variables are independent of one another, okay? Now, if we go back to independence, okay, the idea of independence, if 2 events were independent, so A and B are independent, back at S1, if and only if the probability of the intersection is the same as the product of probability of A and probability of B. That's what we had back at S1. So what we would be assuming, based on the totals, that we would expect 54 out of 500 to have tickets for the zoo only, so 54 out of 500, and 193 out of 500 to be children. And if these variables are independent, then if I multiplied those together, I should get the intersection. Okay? So if I multiply those two, 54 out of 500 and the 193 out of 500, I would be hoping to get something close to this number here. So I work out what that probability is. If I multiply it again by 500, this will give me the expected number that I would get if they are independent. And I get 20.844, which, as you can see, is reasonably close to the number that I've got in that cell. Okay, so how we work out that expected value, and in a quick way, is using this formula. Okay, so from before, we had the 54 out of 500 times by the 193 out of 500 and times by 500, because that gives you the probability, that gives you the expected number out of the 500. So one of those 500s can cancel with that one, which leaves you with the calculation of 54 times 193 divided by 500. So it's easier to just use this formula instead. Row total times column total divided by sample size. Okay, that is one that you need to remember. Okay, you need to remember that's how you calculate it. So we've got the first one. You now need to work out the rest. Make sure that when you've done a total, when you've done your the numbers in the table, you fill in the total row and column again, because that is the check that you've done it right. Okay, the totals should be precisely the same as what they were originally. So what we've done so far is we added up, got the totals, we've now got the expected numbers. So we've now got two tables, the observed values, the expected values. So we now need to make a comparison between those two, okay? And that's where the Chi-Squared Statistic comes in. Now this is used to look at the difference between the observed and expected scores. And the Chi-Squared Statistic is the sum of these, where these are the observed frequencies, the expected frequencies. Okay. However, we need to work out each of these by themselves, right? So we need to fill in this third and final table, which are called the contributions. So how much each one contributes to being significant, effectively. So without that summation symbol, you need to calculate each of these for each of the values that are in the table. You should be all right. You should be all right. So what you'll need to get, for example, for the first one, is the first observed value. So that was 22. So that's the observed value. And then the expected value was 20.844. And so what we need to do to get the contribution is to do the observed value, take away the expected value, squared, divided by the expected value. Now, if you're wondering kind of like where that's coming from, well, it's kind of always coming back to that standard deviation formula again, really. It's finding the difference. That's going to get you negative values and positive values, which will cancel each other out. So you square them to make them all positive, and then we're dividing by this value, the 20.844, in order to scale them down. So we need this as our initial value in the table, 20.844, and I make it as 0.0641. Okay, so that would be the first one in your table. You need to work out the rest. So last but not least, with this formula is given to you in the formula booklet on page 8. Middle left-hand side of page 8, you're given this formula, so you don't need to memorise this, but it has that summation at the beginning. Right, you've worked out all the individual ones, so you now need to add them all together. Okay, right, so we went through finding the totals of the rows and columns, then we did the expected frequencies, then we did the contributions, then you've got to add them all together, okay? Plenty of opportunities there to go wrong, okay? We get this final chi-squared statistic of 17.02. So where does that leave us? Okay? That leaves us with the final hypothesis test to learn for S2. Once again, we're in a situation where there is no parent population to deal with, okay? So what we need to write down is in words, much like it was for Spearman's, and we say that there is no association, so just like Spearman's, between age group and type of ticket. Okay? And what the manager's trying to determine, is there an association? So, H1 is there is an association. Age group. Now, before we can go any further, in order to compare it with what is in the tables, okay, so the tables for this are on page 23 of the formula booklet. So if you could have a look at those now. So the tables are on the left-hand side, okay. Now, one thing that we don't know is what this V value is. Now, it's not actually a V, it's a Greek letter, the Greek letter nu. Looks like that, okay? And it represents the degrees of freedom. Now, nu. Yeah. So the degrees of freedom is quite a straightforward thing to calculate, not as easy a thing as to actually explain what it is, but I will show you in a mo, okay? For a table, all you do is you look at the table that you're dealing with, you subtract one from the rows, number of rows and the number of columns, and multiply it together. So in our case, we had, what did we have in ours? So we've got 3 columns and 4 rows. So we just do 2 times 3. So the number of degrees of freedom in our case is 6. So if we were sticking at a 5% significance level, just as a bog standard, okay, you will never need to look at the p-values that are 99, 97.5, 95 and 90, okay? You won't need those, okay? We're only going to look at the right-hand side set of values. So you look at the 5% significance level, okay? 5%, you go down to new is 6, and that's 12.59. So the critical value is 12.59. Okay. For a Chi-Squared distribution hypothesis test, these are always the same null and alternative hypotheses. Okay? They're always going to be there is no association and there is an association. So it's quite easy to revise. Don't think that because there is an association that makes it two-tail and then you start halving the significance level. Okay? For the Chi-Squared, that is not the case. Okay? We don't look at the two tails for this. So don't start getting confused on that part. So what we then say is, well, effectively in your line, okay, your number line, you've got a critical value of 12.59, and we've got a test statistic of 17.02. So that is within the critical region. It is beyond the 12.59. Okay, and so we reject H0. And there is evidence to suggest at the 5% level that there is an association between age group and type of ticket. Okay? So that's the hypothesis test. It's very similar to what you've dealt with before. The only thing is that you've gone through all that work to get down to that Chi-Squared statistic. But the actual test itself, once you've got that value, is very straightforward to do. Okay? Very similar to what you've had to deal with. So I said that I would just explain the degrees of freedom thing. I'm just going to go with an example for you so that you can see where it kind of comes from. So a basic example is this. Let's say that a data set has 5 numbers and I tell you that they add up to 20. Okay? How many of those numbers do I need to tell you before you can figure out the last one? 4, right? I need to tell you 4 of them in order for you to be able to figure out what the 5th one is. So if it's in a two-way table like the one that we've done, think of it as how much information do we need to be in the table to fill the rest of the table in. So can you fill in the rest of the table? Now? Still not? You can fill in C, SC. Now? Now? Yes. Right? So now you can then say, okay, well, actually, I can now fill in the rest of the table, and we would say that the degrees of freedom in this case would be the 2 times 3. That's where the formula kind of comes from. It's kind of giving you an idea of how much information you have in your table. So those degrees of freedom, as you can see, affects the Chi-Squared distribution, and it changes the shape of the curve. So you've got an example of the shape of the curve in your tables, but as the degrees of freedom increase, it's almost like leveling out, similar to like a Poisson almost, but obviously a continuous version of it. So starting off and moving that way. Obviously the Poisson's not, doesn't have this kind of situation to deal with, but as it continues on, it kind of flattens out. So you've got tasks here where you need to make sure that the table's right. Okay, you're getting all those values in the 3 tables right. You're getting down to your Chi-Squared statistic, and then you're applying it to the hypothesis test correctly. Okay? So, page 92 in the textbook, question 4 to 10. I don't know mind which question you jump to. Your choice. Okay? But you do need to practice it and make sure that you can get all those values right.